choices between problem. But for gallium selenide, you must have local ferromagnetism means you have some local moments.
This
so
is itinerant ferromagnetism.
So you don't have
same as what's happening in iron and so on.
But still you have local.
Well, yes.
Iron has local magnetic moments. You can have.
Yes.
Coupled with itinerant electrons.
There's always a debate on what that is, but here you have all the electrons are extended electrons, and the moment you get out, if you plot the moment density, it will be distributed on each of the, I think the selenium atoms. I have to look back on it. And it's not related to the defects that introduce the carriers in the system. So in that sense, what I mean by itinerant magnetism.
And so also the Bohr magnetron, one Bohr magneton is one Bohr magnet per doped electrons.
Per doped electrons, but they are not, if I integrate around, we have substituted selenium by the outside. We did several things. If you draw a circle around the defect atom, you don't get that one Bohr magneton.
But at least the counting, the total electrons times the Bohr magnetron is basically that's the total magnetic.
Right. Yes.
Just one funnel. So then there's no preferred direction of, it could be just any direction.
There is preferred direction. We also calculate the anisotropy energy. It turns out that at low doping, they like to be perpendicular to the layer. But at high doping, we still haven't figured out why it's actually preferred to be along the layer. And the anisotropy energy, because there's a strong spin orbit in this system, so the anisotropy energy is not that large, but it's discernible. So you seem puzzled. The spin orbit coupling do give you the anisotropy energy.
My question is also about ferromagnetism.
Yes.
Because we're used to an argument that you shouldn't trust Stoner too much. There is Kanamori counter-argument that the interaction will always be suppressed by screening, so it can never exceed Fermi energy, and that's why you can never really go through Stoner transition. So somehow you are saying that it doesn't work in this case. Is it peculiarity of this unusual to be screening, or is it spin orbit?
Well, you're saying that screening will suppress the Stoner yield. Well, this is a fully spin polarized calculation. The screenings are included in the calculation. Screening becomes ineffective for the same reason that I talked about. The field lines are going out of
right.
But if I put it on a very metallic substrate, it's effective.
Right, because that's my. So you're saying it's really. Because Kanamori goes through this argument, but I think for 3D system, and he shows that somehow no, it doesn't really work, that you will always get suppression of interactions that you will not exceed. You're saying if you do it more carefully on this 2D substrate, it actually works. Okay?
Right, it's just a screening thing. I think once you screen away the Stoner parameter, the too low, it wouldn't work. So I would expect that in order to observe this, you have to put it on a nice big gap insulator. Your plasma work is very interesting. You're talking about plasma engineering. One question is that if you want to use plasma for optoelectronic application, your dispersion needs to go above the light cone. I wonder where in your plot the light cone is. In a dispersion plot, light dispersion is linear. So if this line cut through your dispersion, then light will couple with your plasma, and that has a very
unless this occurs, otherwise it's difficult to make optoelectronic device.
Right. I'm not sure. We have not, destroyed the electron there.
Yeah.
But couldn't you use periodic dielectrics to try to fix
yeah,
that?
of course. I was just
Yeah, right.
maybe you
have to put some additional structure to couple it.
Yeah.
Question about massless exciton.
Yeah.
Is there a fundamental origin for the exciton to be massless, or I mean, from high energy, it's quite a miracle to have something which is massless. And in topological insulator, you have masslessness is counted by index theorem, basically. So is there something like this here?
Massless is, I'm using it in a very loose way because it starts with a finite energy and go up like this. So there's no negative energy branch starting at 0. I just find that this is extraordinarily interesting because you have a non-analytic term that's coming out and due to the exchange interactions. So I think it's unique in the sense that it had never been observed or thought of in any 3D systems. And as far as I know, people don't know about this phenomena until now. So I've been thinking and talked to people. I don't think there's any fundamental reason why I cannot have a dispersion relation. I hope that answered your question.
Yeah, I have a curious question about your superconformation. And suppose you start with a wave packet that starts along the y direction, then what would happen?
I think that would, suppose let's not go exactly to y, but small angle away from y. What's happening is we try to guide it to move along the x direction, but then your reflection part, the part that trail, I don't know whether one could see it easily. I could see in my computer a lot better. You turn off the light. There's a tail here. It's like a comic. What's happening is that our understanding of what's going on is that for the you could decompose your wave vector along the direction of the fluctuation and perpendicular to the direction of propagation. Now, if you had in this situation, then most of the wave vectors are moving along the direction. In this situation, most of them are not. It turns out that the fluctuating potential gives you no localization because of no backscattering for a wave vector moving along the direction of the fluctuation. But there will be a localization link. And once the wave of that particular wave vector gone over that localization link, basically the wave will be reflected. So what's happening if you suppose you make this thing infinitesimally away from the y-axis, what you see is you will see still a dot like that, but this dot will be very weak, and most of the lights will be reflected. It's almost like a filter. Right? So this phenomenon comes from the fact that you're moving parallel to the barriers. I mean, perpendicular to the barrier, parallel to the fluctuating direction. There is no refraction. You are just accumulating phase, and there's no localization. But you're moving a large angle, then there is a localization length. So all the big angle wave vectors will be just reflected back. So you just increasing the intensity of this tail. We actually have did a detailed study of the localization length as a function of K perpendicular to the direction of the fluctuation potential.
Am I right? I heard you say that the Qi Chen has done some experiment to confirm this.
Oh no, not experiment. They're doing photonic crystal, a completely different system, and do both analytic and numerical.
Oh, not an experiment.
He's doing an experiment right now, and we have seen the equivalent of Klein tunneling, but we haven't put in the random potential. So we actually put periodic potential and so on. Maybe I shouldn't say that, but that's it's ongoing work.
Follow up on that because the lack of backscattering is because we have the pseudospin.
Right.
In graphene, the pseudospin comes from the equivalence of two sublattices and all the properties of your Blanc wave functions. But when you go to photonic crystals, how do you generate that pseudospin?
That's an equivalent pseudospin associated with the electromagnetic modes of the system. I don't have a picture of it right now, but there is a equivalent of no backscattering. And for the surface states on the topological insulator, you could also argue with real spins. So. Of course, not all impurity, all disorders. The same. There's one caveat here which I didn't have time to talk about. It's in order to not have backscattering, your fluctuation length has to be large compared to the carbon-carbon distance.
Any other questions? All right, if not, let us thank our speaker for this wonderful talk. We will have a team